Thanks for staying. I know it's Friday and you'll want to go to the reception and get some food, so I appreciate you being here. So I'm going to talk about optimal algorithms for distributed optimization. And this is a joint work with Sumin Lee at Yahoo, Alexander Gaznikov at MIT in Moscow, and Professor Angelia Nadish at ASU. So I'm going to start with a disclaimer that I'm being forced to do more often recently, which is this talk is not about deep learning. So just to settle down expectations. So I'm going to start referring to the general problem of risk minimization, which I think is at the heart of most of the learning algorithms that we see recently. And the general problem is that we want to minimize the risk, and the risk is measured at some expectation of loss of some jointly distributed random variables. In this case, could be like the data and the labels. And of course, we generally don't know the joint distribution of these two random variables, so we are forced to go to the empirical risk minimization, which is we are given some data, and based on the data, we want to minimize the empirical risk. So that's find a predictor that minimizes the loss in some way. And the big jump, the theoretical jump or conceptual jump that I'm going to do is that you could see this function. So it's a sum of individual functions that depend on I. So I'm going to talk from here onwards about this function, right? So instead of talking about risk minimization, I'm going to talk about general sum of functions, and I'm going to assume they are convex. So this is the problem that I'm going to be focusing on. So we want to minimize a sum of convex functions. So next I'm going to introduce the distributed setup. So imagine now that we have a network, as you can see here. So each node could be a computer or a machine or whatever you want to call it. And in each of these machines, you have a portion of the data that you have. So this is related sort of to the first talk that we saw. And the data is distributed on this network. And you want, again, to solve this optimization problem, but you have the difficulty that each node only knows a portion of these F, particularly only knows one of them, but they can communicate with each other, and this communication is imposed by a network. So you have some network that imposes the communication constraints between the agents. And we're still want to solve this optimization problem based on local information and communication over the network. And our objective is going to be solve this problem using only local information and achieve convergence rates that matches that as if we had all the information at a central location. Or if we cannot do that, what's the best we can do based on the topology of the network. So this is what I'm going to talk today. And I'm going. And the way I'm going to capture the interaction of the graph itself is going to be through the Graph Laplacian. So in here I have an example of a graph of 5 nodes. And the Graph Laplacian is no more than a matrix where the diagonal is the number of neighbors that each node has. And it has a -1 at every index where you can communicate to. So for example, this agent 1 has 2 neighbors and can communicate with 5 and 2. So I have a -1 and 1, and I have a -1 and 5. So this is, one interesting thing or just thing to know is that the set where all these, each of the entries are equal is in the null space of W. So W times X is equal to 0 if and only if all of them are equal. And this also holds for square root of W. So the way I'm going to approach this problem is I'm going to reformulate it again. So we have sum of functions. So I'm going to introduce this new variable, x, which is m copies, m being the number of agents. So I'm going to have m copies of this variable, one on top of each other. So it's going to be a very long vector. And I'm going to write the problem as minimization of this f, where this f is, again, the sum, but each one with a specific portion of this long vector as an input. And I'm going to have the constraint that, in this case, square root of Wx is equal to 0. So this constraint, as I showed before, guarantees that all of the chunks of this variable x are equal. And if this happens, solving this reformulated optimization problem is the same as solving the original one. I've just introduced an additional constraint and a such things around. So the problem hasn't changed. And in this case, this W is this Kronecker product, but you can still see it as the graph Laplacian. So nothing has changed here. So in this talk, I'm going to study distributed algorithms for solving this problem over networks. And I'm going to present optimal algorithms for this. So in this case, I'm going to show the worst case convergence rate for the best algorithm over the space of algorithms, distributed algorithms, and the space of graphs. So that's what's the worst that can happen. And I'm going to explore this for 4 cases. So when the functions are strongly convex and smooth, strongly convex and Lipschitz on a bounded set, just convex and smooth, or just convex and non-smooth. So my claim is that these 4 cases pretty much holds a huge chunk of the type of functions that you can encounter in the optimization, many of the learning problems that you have, right? And I'm going to call mu the minimum among all the agents. L is the smoothness, which is the maximum among all of them, and the Lipschitz function is the maximum again among all of them. So I'm going to study these 4 cases. So what do we have in the literature? So in the centralized case, we have the work of the oracles, which are Nesterov, Namirovsky, and Yudin. And they show for the 4 cases what's the best you can do. And this table just, I'm going to mention, these are tilde O estimates, so I'm ignoring log factors, just to be a little bit more clear in the presentation. So for each of the 4 cases that I want to analyze, we have the best we can do for the worst function that you want to optimize in the centralized case. So this is known for many years now. It's sort of the point of reference. And in the context of distributed algorithms, there has been a huge chunk of work about different ways to solving one problem or the other and different ways to characterize. And some of them have theoretical performance better than the others. Some dependencies on the number of agents M, et cetera, et cetera. And in this work, what I'm going to show is a bound, a worst case bound for all these cases. And we're going to show basically that we can match that result of Nesterov and Namirovsky with an extra cost of M being the number of agents in the network. So basically, you can solve one of the optimization problems that I showed before, exactly the same as if you had all the information in a central machine, with an extra cost of M being the number of machines that you're working over, in the worst case. It's accuracy, yeah. Closeness to optimality. Yeah. Right, because I'm ignoring log terms. So the epsilon is inside the log. Yeah. And for example, in those results like here, so they have this result on epsilon, but they don't have any characterization on M or L. So this is sort of... So what we have here is that we have an explicit characterization on the problem parameters and the topology of the graph, which is... so, yeah. Oh, yeah. So in here we have a square root of this value, which is square root of what Nesterov says. So you could say that we're doing better than Nesterov, which is impossible, but it's under some constraints. So that's why the title is a dual approach. So because we're translating the problem in the dual space, computations or calling the oracle means communication rounds, so agents talking to each other, not computations of the gradient. So these bounds are for computations on the gradient on the primal space. So these are bounds on the dual space. But
I guess when you convert back to the problem, that's
exactly. Yeah, when you consider also these gradient computations, we also match these ones. Yeah. Right. So I'm going to introduce some analysis tools, very simple. So initially, we're going to consider this simple optimization problem. So it's a minimization of a function with linear constraints. So nothing new here. And then we're going to see what happens when A is square root of W, and what happens with F is the sum of the functions. So, but first I'm going to consider this simpler problem. And I'm going to define an approximate solution like this in terms of this. So when our function is epsilon close to the optimal value. And I'm also going to consider this, which is distance to sort of consensus. So how far are the values of each of the agents? So I'm going to have this definition of epsilon tilde epsilon solution if these 2 conditions hold. So This is going to be my definition of optimality. So I'm going to recall again how can we move the problem from the primal to the dual. So very simple. This is the primal problem. I'm just going to construct the Lagrangian, which is defined like this. So equivalently, we have the dual, which is again another minimization problem. But this function itself, var phi, is defined as another maximization problem. So this is the dual problem. But what is interesting is that when we have these linear constraints, the gradient of the dual function is A times X star, and X star is the arcmean of this inner minimization problem. So we have, let's say, an explicit form for the gradient. Even though it's an optimization problem itself, we can calculate it. And we're going to call a function f dual friendly if we can compute this value relatively fast or up to some accuracy relatively fast. And this is where the square root comes from, right? So when you have some delta approximation here again, then the square root pops out there. So initially, we're going to consider dual friendly functions, which are functions for which we can compute this relatively fast. And our main analytical tool also is going to be like if f is strongly convex, then the dual problem is smooth. But then we also see here the maximum eigenvalue of A transpose A, which are the linear constraints. And if f is smooth, then the dual problem is strongly convex. And the strong convexity has the minimum non-zero eigenvalue of A transpose A. So this is some duality between the primal and dual spaces. So if you have a strongly convex, you move to smoothness. And if you have smoothness, you move to strongly convex. And again, just for the experts in the room, the dual problem might have multiple solutions in the kernel of the linear constraint. So we're going to denote y star, the one with the smallest norm. And we're going to call the norm R. Right. So again, we have the dual problem. And again, this is another remark for the experts in the room. So even if the primal is smooth, the dual is strongly convex, but not in the whole space. So this is something that we need to deal with. But choosing some correct initialization in the optimization algorithm, we can guarantee that the solution always lives on the space where we have a strong convexity. So this is just technical results. And this is Nesterov algorithm for the dual problem. So we have moved to the dual problem, and we have written what Nesterov does. So we compute the dual friendly function here. We take some gradient step, and then we use momentum. This is nothing new. This is Nesterov algorithm, just that I have written it for the dual problem. And then we have some bounds on the performance of the algorithm, how far we are, right? So now we're gonna start replacing the values. For example, we know A is square root of W, the graph Laplacian. And if we replace just the square root of W here, we cannot guarantee that the sparsity pattern of W is the same as square root of W. So in theory, just replacing A here cannot be executed over the network. So what we're gonna do is a little bit more complicated. So we're gonna replace A, but we're also going to pre-multiply all these variables by the square root of W. So nothing's going to change. It's just that what was here initially square root of W is going to be pre-multiplied by another square root, and it's going to transform just in W. Right? I've done nothing strange. I've just rewritten the variables here and there. So we can rewrite then Nesterov algorithm. But what is interesting here now is that this algorithm can be executed in a distributed manner. So what each agent is going to do is it's going to solve the inner minimization problem of the dual, and is going to share this solution with its neighbors, and then he's going to aggregate the solution coming from the neighbors. So again, this is only those links that are activated, so those J's that I can talk to, and then introduce the momentum. And in all these three steps, each agent only requires local information. So even though we didn't intend it from the beginning, just by parsing the problem into the dual, we have constructed an algorithm that can be distributed over the network and can be executed. So this is the main idea, and the technical contribution then is how to parse an optimization bound on the dual, the optimality bound on the dual, into our definition of approximate solution on the primal problem. Okay. Non-zero, because it's the graph Laplacian. So the smallest non-zero eigenvalue, yeah. So we have the 4 cases, and I'm already running out of time. So the next thing was going to show the 4 theorems for the 4 cases, right? So I'm just going to ignore all of them and go directly to the summary. So the summary says that we can get exactly the same bounds for the 4 cases as nested of, with an additional term here, chi of w, which is the condition number of the graph Laplacian. Right? This is the theoretical bound. And then we can build upon the recent work by Alex, which shows that for fixed undirected graph, the worst case condition number that we can get is m squared, of the order of m squared. So because we have square root here, then the bound translates only on linear dependency on the number of agents. Right? So what we have shown here is that you can solve any distributed optimization algorithm over the network and get sort of the same rates as the centralized version by paying only a linear price in the number of agents. And of course, if the graph is much better, for example, if you use like Erdos-Renyi graphs, for which the condition number is like log m, then you could say that you perform as good as a centralized algorithm. And just to mention a little bit about the proofs, what we're going to, I mean, the main idea is, okay, when we have strong convexity and smoothness, sort of follows immediately from nested of. When we have strong convex functions, we can regularize the dual, and then the dual is going to be, so the dual originally is smooth, and then we regularize, then it's smooth and strongly convex. When we have only smooth functions, you can regularize the primal, and then it's going to be smooth and strongly convex, and the dual have the same properties. And in the case of only convex functions, you can regularize the primal and the dual at the same time and get the same bound. So again, this is interesting. One thing to know is that we generally don't know R or the values of R, so you can start some restarting techniques, but we're being cautious on this area. And now proof by picture, I have some time. So the simplest problem that I could imagine is just rich regression. So what I have done is I've distributed all the samples among n machines and tried to solve this over the distributed setup. So top images are when you consider a cycle graph, which performs like m. And the bottom are Erdos-Renyi, which have log m. So I'm going to the left part, which are the scalability of the algorithm. So how much time did you need to solve the problem versus the number of agents? And I'm comparing these with the state-of-the-art algorithms. Our color is blue, which you can not see, but it's here, right? It shows it's linear, and it's better than the others. And as you can see here, right? And the same happens for Erdos-Renyi, and you can see also geometric convergence on the optimality and the consensus. So we can get good results. And again, I have examples for all the other cases, but I'm not going to deal into that. Yeah. So this is it.
Right. Questions?
Have you thought about time-varying graph?
No, we don't. It's an open problem. Yeah. The good thing about primal approach is that you can deal with time-varying and directed graphs, but you cannot say much about the optimality of the results, the optimality of the bounds, right? But in the dual, we can say about the optimality, but we have no idea how to handle time-varying or directed graphs. Yeah, we don't know.
So, in cases where, like, if some nodes have much higher degree than others, let's say a star graph, right? You can imagine a trade-off of sort of computation and communication. Like, one thing is everyone send to the center just does all the work, lets everyone know. But then they're doing all the work. Does it kind of make sense to think about?
Right. One key thing, one assumption that I didn't mention is that the nodes are oblivious to the topology of the graph. So they don't know how the graph looks like. Of course, if they know it's a star graph and they know they're not the center one, then they can sort of relay some computation to the center or vice versa. But in here, the nodes only know they have some neighbors, but they don't know the whole structure. So they are oblivious to the topology of the graph.
So what about in learning problems? A lot of times the optimization is done in a stochastic way, right? So does any of this extend to stochastic optimization?
We haven't done the proof for that, but we have a strong belief that it just extends immediately because so the work of George Land, he extends the complexity bounds on the centralized case to the decentralized case. So they have the same complexity bounds for stochastic problems, optimal ones. And so we could just I'm waving, right? But we think so, yeah. They're just extend. Yeah, exactly. Or in expectation, not almost sure. So, yeah. So in the case of stochastic programming, same bounds but on expectation.
Two questions. So first, is your lower bound for any condition number, like what Nestor does, or just for specific number, like worst case M?
Yeah, worst case.
So that's a different lower bound.
Right.
Okay, in a weaker sense.
Yeah.
Okay. Another question is, so you have Laplacian for the matrix, right? Mm-hmm. That kind of lower bound worries me a little bit because we know that it can solve Laplacian linear system in a much faster way than traditional methods.
Right.
You probably know the recent progress.
Yeah.
So I was wondering, probably it's not the optimal way to just solve in like Nestor's gradient descent.
Right. Yeah. It could be that that could not be that representation of the graph Laplacian as this type of linear constraint might not be the best option, right? What we care about here is that when you move to the dual, the algorithm itself can be executed in a distributed manner.
So I think I'm referring to the recent progress of Spielman and Tang on solving Laplacian linear system in linear time.
Right.
So I think if you have a graph Laplacian kind of structure in the AX equals 0, you should explore the structure to solve it much faster.
Right. Yeah, I mean they could be other options. So
yeah, so that's why. So why do you have a lower bound of? This kind of lower bound is a bit restricted. But I haven't fully understood in what sense is restricted.
Oh, okay.
Yeah.
So for the case of the graph Laplacian, the lower bound that we use particularly is this one. So, if you could solve the distributed computation in linear time, that we can replace that bound. But I'm not sure of the details at this time. But we have used Olszewski, which it shows. And I think it's important to point out here that we don't know the topology of the graph. Right? The nodes do not know the topology. Yeah, okay, yeah.
Let's thank the speaker one more time.